Question 7 then. So we have our trolley and card and light gates and everything else that you can clearly see in the picture. And we were asked first of all why the trolley is going to accelerate along the track. I mean, the obvious answer is because of this guy here. But you need to explain that in slightly more physicsy terms than because of this guy here. So if something is going to accelerate, first of all we know there must be an overall force on it. Why? Because F equals ma. You've seen this equation before. If you're getting an acceleration, you must have a force. It's as simple as that. So there must be an overall unbalanced force there, or an overall resultant force. Where is that coming from? Well, we've got the weight of the discs here, haven't we, pulling down. That's going to result in tension in this string. This string is going to be pulled tight by these weights here. That tension is going to be pulling this trolley along. And if it's moving, which it is, we know, because it's accelerating forwards, that force this way must be bigger than any force that way. So any sort of friction or whatever, any air resistance that's trying to slow it down, it's not as big as the tension pulling it forwards, or you could describe it as the weight of this pulling it forwards. And we know that because it's accelerating along the track. So according to the mark scheme, unbalanced resultant force of 1 mark provided by the tension in the string or the weight of the metal disc for the second mark. We now get to a calculation one, and again we're given numbers, so let's work out what the numbers are. Not so much work out as look at them and write them down. We know that the time is 0.04 seconds. We also know that the average speed of the trolley V is going to be 1.15 meters per second. Might as well stick the unit in for that if we've done the same for time. We're going to try and work out the width of the car from this. This is just a straightforward speed is distance over time kind of equation. So we know that the velocity or the speed of something is equal to the distance travelled divided by the time. Now let's use, in this case let's use x. Doesn't really matter. Sometimes we use x, sometimes we use d for distance, whatever. So it's distance divided by time. We're going to try and work out how far it's travelled. Now of course, if you imagine that this is, let's go back to our picture, so we've got that thing going through here. The width of this card is the distance that it's travelled during the time when it's been going through this gap. So if you imagine that this graffitied board rubber is the card, as it goes through, there we go, as it goes through the light gates, the light gate beam is broken here, and the timer starts, and then the light gates beam resumes here, and the timer stops. So the distance we've travelled is this distance here, the width of the card. So we bring our maths back again. V is x over t, speed is distance over time. We want to work out distance, multiply both sides by time, and we'll get our answer. Vt is x. We're going to have the speed times the time, 0.04 for the time, 1.15 for the meters per second for the speed. Multiply the two together and you will get your answer, or will you? If you do it, you'll end up with a value of x of 0.046. But they've been a little bit sneaky here, very sneaky in fact, because they've forced you to put your answer in centimetres, even though it hasn't been mentioned in the question at all. But you've noticed it here, and you're thinking, this calculation has worked out the distance in metres, hasn't it? We've done meters per second times by seconds, it will give us meters. So we need to put this into centimetres. There's 100 centimetres in a metre, so we need to times this by 100. So it's going to give us 4.6 centimetres. Fair few of you managed to get this far. There was a few that missed that crucial last step, so you may only have got 1 mark out of 2 just for that question. So 4.6 centimetres for that one there. The next one's a show that, interestingly. I'll show you maybe a couple of ways of solving this one. You've got to prove something, so they're asking you to prove that what they've said is true. The first way you can do it is you can assume that what they've said is true, and show that it's consistent. You'll see what I mean in a moment. So we're given the trolley travels 1.2 meters along the track. So there's our distance, 1.2 meters. And from the start before the car reaches the light gate, so we're trying to show the acceleration is going to be approximately 0.55, so approximately equal to 0.55 meters per second squared. Okay. What else do we know? We know that it starts at rest. It is not moving at the beginning. So therefore the initial velocity is going to be equal to 0 meters per second, of course. What else do we know? We know the speed as it goes through the light gate, so that would be the final speed, because it starts off at 0, and by the time it reaches here it's its final speed, which is 1.15 meters per second. So v, the final speed, is 1.15 meters per second. So those are the four things that we have. We're going to try and prove this one, that the acceleration is 0.55 meters per second squared. So we need an equation with those four terms in, and the equation we're going to use is v squared minus u squared equals 2ax. You can see all those terms are in there. So v squared minus u squared equals 2ax. We've written our equation into there. Now you don't actually get a mark for writing that equation, but the next stage you will. So you can work out, I mean u squared is 0, of course. You can figure out how big v squared is, and how much this 2ax thing is, and show that they're the same. So v squared is going to be 1.15 squared, because v is 1.15. That gives us 1.3225. And that's of course meters per second. I've run out of space to write that. So v squared minus u squared will be 1.3225. The 2ax thing is going to be 2 lots of 0.55 times 1.2, which comes out as 1.32. So 2ax is 2 lots of 1.2 times 0.55. Acceleration, distance, which drops out to be 1.32. You can clearly see that these two numbers are pretty similar, so therefore the acceleration must be about 0.55. So that's one way of doing it. There is another way, one that is often sort of more favoured in the A level, and either is absolutely fine, and no one way is particularly easier than the other. The other way of proving things is just to calculate it. So if you have A, we want to show that A is equal to 0.5, or approximately equal to 0.55. All they're really doing is asking you, calculate A, your answer should be about that. So we go back to exactly the same equation as we had before. v squared minus u squared equals 2as, or ax in this case. Of course we can ignore the u because the u is 0. So you could then rearrange this. So in this case we've got v squared is equal to 2ax, of course. You're trying to find what a is, so we just divide both sides by 2x. v squared over 2x is equal to a. If you shove the numbers in, so 1.15 squared divided by 2 times 1.2, that will give you a number that is similar to 0.55, and therefore you've proven it. So two ways that you can approach that, show that kind of question. The show that questions are really nice because you will know whether you've done it right or not. Because if you went through all that we've just described there, and the answer that you calculated wasn't 0.55 or close to it, you now know that you've made some sort of mistake, and you can then go over your working and check to make sure that everything's okay. Of course, there's another advantage to writing your working clearly in exams. We should always be doing that. Right, moving on. It's quite a long one, this one. Graph of the results for acceleration of the trolley against the number of discs. Clearly, as we increase the number of discs, we're getting a larger acceleration. But also, noticing this curve of the graph, it tells us that as we start to get to higher numbers of discs, every time we increase the discs by 1, the acceleration is still increasing, but by a smaller amount. So initially, when we start increasing the disc numbers, the acceleration increases rapidly, as we continue to increase the number of discs, it is still increasing, but is it increase? It's an words. It is increasing at a slower rate. Sometimes when people were trying to describe this curve, they said it was kind of decreasing. The rate is decreasing, but the acceleration still goes up every time you add a disc. So careful with that. First off, predict the acceleration if discs with a total mass of 800 grams are used. Let's have a look. Well, 800 grams, that would be 8 discs, won't it? So it's somewhere on here. We've got to work out where this line is going to cross this point here. So for 8 discs, the line is looking like it's going to go sort of around about there. Official answer is 4.4, so just, I don't know if you, you're not really going to be able to see that, are you? The idea is basically that you would just continue this line so it would match up. Some people said 4.5, but in order for that to be the case, you know what? Let's break out the ruler. There we go, shiny. In order for that to be the case, you can see, if I show you where the 4.5 mark is, which is there, see how that would require the line to change its gradient. You can see it's curving upwards, it's going into the ruler there. So it can't be 4.5, you're looking at 4.4. If I lay it on the 4.4 and drop it down a little bit, you'll see that's kind of where that line is going. 4.4. Good. Frictional forces in the system. How can we tell? Well, look at the graph. If I extend the line a little bit further this way, I'll find that if I've got, I don't know, 0.8 of a disc, so at least some weight on it, the graph is suggesting that the thing won't move at all. We would have 0 acceleration if that line crossed the axis there. If I was just having no, if I was putting some masses on. Now what you'd expect if there was no frictional forces is adding just a very, very tiny amount of discs, or a tiny fraction of a disc, would make it accelerate but at a very low rate. That's not what we're seeing. We're seeing that there's a certain amount of discs that you could add, about 0.8 discs, and it just won't budge. So there must be some sort of force which is working against the force that we're pulling it along. We have 0.8 discs here, it's not going to move, there must be some sort of force. It'd be the same size, acting in the opposite direction. That would be a frictional force. Just a single mark for that. So you could describe that, and the mark scheme says if you project the graph back, it doesn't pass through the origin. OWTTE, all words to that effect, is what that means. We would accept not a straight line. And finally, explain how the investigation could be developed to remove the effects of friction. This was a really nice and horrible question at the same time. It's clever, but it is perhaps a little mean, because you had to think quite carefully for this. Here's your problem. Loads of people said, well, if we want to get rid of the effects of friction, we want to lubricate the wheels, we want to remove the friction in the wheels, you want to use a very smooth surface, etc., etc. That can't remove the friction entirely, though. It says how the investigation could be developed to remove the effects of friction. So we want to have no effect of friction at all. Now, you're not going to get a completely frictionless environment. So how else can we do it so that we can remove at least the effect of friction? Well, there's a cunning way that you can do it. You can put the trolley on a slope. So here's your trolley. It's being pulled down by this thing. There's your wheel. This thing comes down. If I put it on a slope, that means that even though I've got a frictional force here, I've got a certain component of this force which is trying to pull me this way. And if I make the slope big enough, simply the weight of the trolley and the weight of this, or really just the weight of the trolley because this is extra, the weight of the trolley itself will be the same size going in this direction as the friction. I'm just going to unpack that slightly more because it's a somewhat complicated idea. If you have a slope and we give it a bit of an angle, some of the force, we've got this kind of weight force acting down here, haven't we? some of the force, most of the force is going to be pulling this thing into the slope, but some of this weight is actually going to be acting along the slope. That's why, you know, if you've got a slope, and I mean, here's a slope, here's an object, if I've got a bit of an angle there, it's going to roll down, because there's a component of that force which is acting this direction to try and move me down. I mean, you've looked at components of forces. Here's the idea. Most of the force is pulling this way, but some of the force is pulling this way, if we turn it into a right angle triangle. So, I mean, that is going a long way to just try to explain the idea that if you tilt the slope, then the effect of the weight of the thing down the slope will counteract the fact that we've got friction there. It won't remove the friction, but it will remove the effect of friction, which is what you were looking to do. So the official answer, raise the left end of the runway, in other words, make a slope, so that the force of gravity on the trolley will balance the frictional forces. Okay, we can't remove the friction, but we can tilt the trolley to remove its effects.